Hello, good evening. I am Shivani Thok and I welcome you for the last, that is 12th week session for the course of Principles of Signals and Systems. So the 12th week cover was a very short, covered very less number of topics which included group and phase delays and IIR systems realizations. So I shall be covering some examples for finding group and phase delay and some examples of how to represent IIR systems using various system realizations. So to begin with, let us do the recap. So the first thing that was introduced in this week was group and phase delay. So the the phase delay is given as tau p of omega naught and it is obtained as minus phi omega naught by omega naught, where this phi of omega is basically the phase of any system response. So if I have an LTI system HT, then its Fourier transform is h of omega and the phase of it is known is phi of omega, and the tau p, that is phase delay, this is phase delay, is given as minus phi omega naught upon omega naught, where omega naught is the frequency of sinusoid that I am inputting to this system. So I am giving cos of omega naught t as an input. And the group delay is given as minus t d omega phi omega, and this is evaluated at omega equal to omega naught. Now if I have an output of the system something like this, that is yt is equal to a magnitude h of omega naught cos of omega m t minus tau g into cos of omega naught t minus tau p. So here this is my group delay and this is my phase delay, and omega m is basically the frequency corresponding to the message signal. So this is message and this is carrier, and this type of system or input output relationship is generally observed at the modulator end of any communication system where any message signal is modulated over a high frequency carrier wave. So it can be observed that this carrier is delayed by phase delay and this message is delayed by group delay. Then another thing regarding this group and phase delay was covered, that was if my phi of omega is linear in omega, then your then the system is known as a linear phase system. So in such case it is a linear phase system, and in this situation my group delay will be equal to my phase delay. So this was all that was covered for covered for group and phase delay, and after that IIR system realization was covered. In that different forms were covered which included direct form 1, direct form 2. So these two are very similar, that is this direct form 2 is obtained from direct form 1 by just interchanging the order of the systems. Then there was direct form transpose 1 and direct form transpose 2. After that there was a cascade form and followed by parallel form 1 and parallel form 2. So an important point to be noted for parallel forms is that for parallel form 1 we find partial fractions. So basically for both of these we find partial fractions, And for direct form 1, we use Z inverse. We find partial fractions form in Z inverse. And for parallel form 2, we find it in terms of Z. So this is the basic distinction between these two parallel forms. And to understand these concepts in a better way, let us consider some examples regarding it. If you have any questions regarding these topics, please let me know. Okay. If not, then let us start with very first question. So it says that the input to a channel is a bandpass signal. It is obtained by linearly modulating a sinusoidal carrier with a single tone signal. So sinusoidal carrier means it is of the form of cos 2 pi, or let's say cos of omega naught t. This is my carrier. And also we have a single tone signal. So single tone signal also implies a sinusoidal signal, that is it has only one frequency. Single tone means one frequency, so it is also of the form of cos of omega m t. And they have given the output of any of that system. Now the carrier frequency is always much larger than the message frequency, so your omega naught will always be greater than your omega m. So if we observe here this 100, so this y of t, which is the output, it is basically of the form of yt is equal to a cos of omega mt minus some uh, phase into cos of omega naught t minus some phase, let's say phi naught. So it is of this form. And now we need to find the group and phase delay of this signal. And here this omega m is 100 and this omega naught is 10 raised to 6. Now in order to find group and phase delay, if we compare this yt which is given here with what we have written here, and so it is basically a similar representation. The only thing is the delay is of the form t minus tau g. So basically we will need to take common this omega m and omega naught from this form in order to get my tau p and tau g, that is group and phase delay. So let us do that. So what we are having is yt is equal to 1 by 100 cos of 100t minus 10 raised to minus 6 cos of 10 raised to 6 t minus 1.56. So this I can write as 1 by 100 cos of, I can take out 100 common, t minus 10 raised to minus 2 into 10 raised to minus 6 cos of 10 raised to 6 common, t minus 1.56 into 10 raised to minus 6. So now this is my omega m and this is my omega g. Now we know that the envelope is so this is known as my message. So this message is basically delayed by group delay. So this is my message and this is delayed by group delay. So this is my tau g and the carrier is delayed by phase delay. So this is my tau p. So my group delay is 10 raised to minus 8 seconds and my phase delay is 1.56 into 10 raised to minus 6 seconds. So these are my group and phase delays.
Madam, what is the omega G? Omega G, that is omega naught, right?
Sorry, omega naught. Yeah. Any other questions? Okay. So now let us look at another question. I'm sorry, this is HD. Yeah. So I have been given the impulse response of two systems, and let's say I have a single tone input or frequency omega naught, and I need to find the group and phase delay for this. So we know that the phase delay tau p of omega naught is given as minus phi omega naught upon omega naught, and tau g of omega naught is given as minus dt omega of phi of omega evaluated at omega equal to omega naught. And we'll use these two formula to find the group and phase delay for this system when I'm having a sinusoid as an input. So now ht is del. So let's start with the first one. So this ht is delta t minus t naught. So the Fourier transform of this will be h of omega. This is continuous time Fourier transform. It will be e power minus omega t naught. So this is basically coming with a g. I'm sorry. Yeah. So this is basically coming from the time shift property. So now if I look here, then angle of h of omega, which is phi of omega, it is equal to minus omega t naught. Okay. Then my phase delay, that is tau p of omega naught, will be simply equal to minus of minus omega naught t naught, which is equal to omega naught t naught divided by omega naught, which is equal to t naught. And my group delay will be tau g of omega naught, and this comes out to be minus dd omega of omega t naught with a negative sign. So this comes out to be t naught. So now if you observe carefully, this phase, that is angle of h of omega, that is phi of omega, is basically a linear function. So this is linear phase, and you can observe here that my tau p of omega is equal to tau g of omega. Therefore, for a linear phase system, the group and phase delays are equivalent or equal. Now let us look at the next part of this question. Okay. So the second part of this question is ht is equal to e power minus t by rc ut. So this is our standard exponent, which is of the form of e power minus at ut, and we know that the Fourier transform for this is h of omega equal to 1 upon j omega plus a. We have seen this previously, and here a is equal to 1 by rc. Therefore h of omega will be equal to 1 upon 1 plus j omega plus 1 by rc. And now we need to find angle of h of omega, which is equal to phi of omega. So that will be equal to angle of 1 minus angle of j omega plus 1 by rc. So this is basic. Angle of 1 is 0, so this is 0 minus this is.
Madam, see, I am, can you just explain how to compute that phase? I know this is fundamental high school math. Okay, I just forgot. Phase of that h of omega. You said angle of 1 minus angle of just to make me recollect the formula.
Okay, fine, no problem. So if I have any number, which is of the form a by b, and I need to find angle of this. Let's say it is a complex number a by b, then this is basically the phases get added. Like if I have a b, two numbers, then phase of these two get added. Okay, so let me write it. Okay, fine. I will use something different. So okay, this I can write as, let's say this j omega plus 1 by rc has some magnitude. Let's say this is a, so this will be having some magnitude a, and it will have some angle, something like this. Okay, so this is equivalent representation of this number. So this h of omega I can write as 1 upon magnitude a into e power j angle a, which I can write as 1 by magnitude a into e power minus j times angle a. Now this 1 is a constant. Now if I draw it on a complex plane, so this is my real axis and this is my imaginary axis, then this 1 lies here. So with respect to this 0 axis, this 1 makes an angle 0. Similarly, if I have a minus 1 here, it will make an angle of 180 degrees. If I have j, this is j, then it will make an angle of 90 degrees. If I have minus j, then it will make an angle of 270 or minus 90 degrees. Just a minute. Yeah. Okay. So now this 1 I can write as, so this I can write as e power j 0 into e power minus j angle a upon magnitude a. So now if you observe, these two are simply in multiplication. I can write it as j times 0 minus angle of a. 0 minus angle of a. So it is same. This is angle of 1, which is equal to 0, minus angle of a, which is 1 by which is j omega plus 1 by rc. Is it okay?
Okay, madam. Okay. So the phase of j omega 1 by rc is we have to calculate.
Yes. Phase of, sorry, I didn't understand. Can you
Yeah,
repeat?
the phase of j omega plus 1 by rc.
That we need to calculate. Yes, that we
Yes,
need
yes.
to calculate. And phase of any complex number, let's say I have z equal to a plus jb, then angle of z is always given by tan inverse of b by a. So this comes out to be tan inverse of imaginary part is omega by 1 by rc. So this comes out to be omega rc. So this is the phase, that is phi of omega. Therefore, if I calculate my phase delay, so my phase delay tau p of omega naught is given as phi of omega naught with a negative sign upon omega naught. So this is tan inverse of omega naught rc by omega naught. And this group delay tau g of omega naught is basically minus td omega tan inverse with a minus sign here omega rc, and this will be evaluated at omega equal to omega naught. So the differentiation is 1 upon 1 plus omega square r square c square into rc to be evaluated at omega equal to omega naught, which comes out to be rc upon 1 plus omega naught square r square c square.
Madam, omega naught is the fundamental frequency, right?
Omega naught is not the it is the frequency of your input sinusoid to your LTI system.
Oh, okay, okay, okay. Omega naught is, yeah, omega is equal to omega naught. Okay.
This is the
Yes,
starting
yes,
point of
yes.
our derivation for
Oh, okay, okay, okay.
yeah.
Thank you.
Or let's say it's an operating frequency of your system. That is, it is operating at that particular frequency. Like suppose I have an RC circuit, and then I am connecting some voltage source to it. The voltage source is of that particular frequency, omega naught.
Okay, madam.
Yeah, okay. So this group and phase delay is a very simple concept, and these are the two examples that I wanted to cover. If you have any questions in this group and phase delay part, please let me know. After these two questions, I'll move on for system realization part. Okay. So, as I mentioned earlier, there are there are total 7 ways in which I can do system realization. There are more ways, but here in this course, these 7 ways are considered and explained. So, for a given impulse response or for a given transfer function, we'll now try to represent it in all these 7 forms one by one, so that it's clear. So the first way in which we will do it is the direct form 1 and direct form 2. So let's start with this direct form 1. So for that, what I'll do is, okay, so here we have been given yz upon xz is equal to 1 plus 2z inverse upon 1 minus 3z inverse plus 2z in z to the power minus 2. So this I can write as yz multiplied by 1 minus 3z inverse plus 2z to the power minus 2 is equal to xz into 1 plus 2z inverse. Now if I take its inverse z transform, then I'll have y of n minus 3 times y of n minus 1 plus 2 times y of n minus 2. This is equal to xn plus 2 times x of n minus 1. Now I can rearrange it such that I have yn is equal to xn plus 2 times x of n minus 1 plus 3 times y of n minus 1 minus 2 times y of n minus 2. And this is the equation that we will use okay, is the content that I'm writing visible? Yeah, okay, fine. So this is the equation yn equal to xn and so on. This difference equation is the equation that we'll be using in order to draw our direct form 1. So let's start with direct form 1. So here let's say we are having this input x. So this is x that we are having. This is xn. Now along with that, I am having a delayed version of this xn. So this delay is characterized by this z inverse block, that is unit delay block. So here I am getting x of n minus 1. So this is x of n minus 1, and this gets scaled by a factor of 2. So this is a gain block. So this is factor of 2, and this gets added with xn. Okay. So here at this point what do we have? xn plus 2 times x of n minus 1, and we need something more to be added to this to get yn. So let's say this is my yn. So what gets added? So it is basically a delayed version of yn. It gets scaled by a factor of 3. Also there is another factor which is delayed by one more unit. So basically here I am having yn minus 1. So yn minus 1 when delayed by one more unit, so it will give me y of n minus 2. So this yn minus 2 is scaled by minus 2, and this gets added here, this gets added here. So here what I have is, here basically I have y of n minus 1 which is scaled by minus 2. Here at this point I have 3 times here yn minus 1 minus 2 times y of n minus 2. This is minus 2, and here at this point I get my y of n. Are there any questions in this direct form 1 representation?
So direct form 1 actually stops with this, right? This is direct form.
Yes.
So you directly look at the difference equation and then you construct it.
Yes.
Okay.
Then then the direct form 2 is obtained by just interchanging two subsystems. Like if you observe carefully, this part here can be considered as one subsystem and this part here can be considered as another subsystem, and we know that convolution is commutative, so we can just interchange these two in order to get my direct form 2. So that's
Madam, can you explain that? Okay, subsystem 1 and subsystem 2, how it is convolution and interchange?
okay. If you look at this point here, this I can write as 1 minus 2 1 plus 2z inverse multiplied by 1 upon 1 minus 3z inverse plus 2z inverse.
Okay.
2z to the power minus 2. So this I can consider as h1 of z, and this I can consider as h2 of z. And
Yes.
this is my h of z. Now this
Yes.
h of z is basically h1z into h2z. This I can also write as h2z into h1z.
Yes.
So right now what we are representing is this part is h1.
Yes.
And this part is h2.
Yes.
So now instead of doing this, what I'll first construct h2 of z and
Yes.
then cascade it with h1 of z. So basically I'll interchange these two.
Okay, so first you start with y. No, y and
No. We'll start with
okay.
x.
Okay.
See,
Okay.
to your this is just your system hz. I'm just interchanging this part between my input and output. It won't change.
Yes. So you start with the one by one minus yeah.
Yes.
Yes. Okay. Okay. Go ahead, madam. I can understand.
So let's start with direct form 2. So I'll just take this part and draw it here, and then the first part, and so what I have is, here I have xn, z inverse, then I have a gain block of 3, then I have this z inverse, then this is minus 2, this goes here like this. Now I'll construct this part. So I have here one adder, and this part goes through a delay which is already present here. So I won't add another delay block, and I have this here, and it goes like this. So this is my y of n. This is my direct form 2 representation.
1 minute. I get confused. Can you illustrate 3? Okay, you have written 3. It should be -3, right? For the amplifier.
No.
Can you just explain? No. How could you come out with this from the equation, from the expression 1 by 1 minus 3z minus 1 plus 2z minus 2?
Okay. 1 upon 1 minus 3z inverse plus 2 z to the power minus 2. How will you construct this? I have
Yes.
xn. Okay, let me do it more. Let me add. I'll keep this as it is. I'll add another page. Okay, so the equation that I have is hz is equal to 1 upon 1 minus 3z inverse plus 2z to the power minus 2 multiplied by 1 plus 2z inverse. Okay, so let us consider this h1. H1 of z. So it is basically, let's say it is, this gives me this system. It is something like this: h1 of z followed by h2 of z. Let's say the output of this is w of n, and this is x of n. So this is basically wz upon xz. This I can write as 1 upon 1 minus 3z inverse plus 2z to the power minus 2, which implies that my wz into 1 minus 3z inverse plus 2z to the power minus 2 is equal to xz. So my xn is equal to wn minus 3 wn minus 1 plus 2 wn minus 2. My output was wn, so I can write it as wn is equal to xn plus 3 times wn minus 1 minus 2 times wn minus 2. So what I have is, this is my xn, this is as it is, and this something gets added here to give me wn, and it is basically my delayed version. So I have a z inverse here, then I have a delay block of 3, again I have z inverse and a delay block of minus 2, a gain block of minus 2, delay block of unit, and yeah, this gets added here. This is okay?
Okay, madam, I got it.
This is exactly the same thing that I have drawn here.
Okay. So, we have modeled as by having a W in between transfer function.
Yes. Okay. Shall I go more deep into this, like how to cascade it? Okay, I'll do it for one example, and then for the next one I'll just use it. So this wn is basically input to my, so what is remaining is I have this wn, which is input to h2z, and output of this is yn. So what I have is yz upon wz is equal to 1 plus 2z inverse. So this yz is equal to 1 plus 2z inverse multiplied by wz. So this I can write as yn is equal to wn times w of n minus 1. So if we observe carefully, this is wn that we have obtained, and this point here, this is basically w of n minus 1. So what we'll do is we'll take this wn here and take this wn minus 1 and multiply it by a factor of 2, which is here, and then add it, and this will give me my yn.
Okay, madam, I got it.
Okay, so this is how basically your direct form 2 is constructed. So this is what we are having here. This is direct
Uh,
form 2.
just a minute. So, what is the fundamental difference direct form 1 and 2? If you look at it, look at the structure, it is the same thing. Input is xn, output is yn. Okay, some manipulation we have done, right?
Yes.
Some left and right.
Yes.
Okay. So, what is the purpose? Like, what is that we are gaining, or which one is better, and why we do that?
Okay, so basically when I need to realize any system, the fundamental components of it are my electronic circuitry, which will basically correspond to some adder, delay blocks, and amplifiers. These gain blocks are basically my amplifiers or attenuators. Now, if you observe carefully in these two, so if you look at the gain blocks, those don't change. Like this 2, 3 and minus 2, 2, 2, 3 and minus 2, these are same. But the number, even the number of adders are 3, 1, 2, 3, 1, 2, 3. But what I'm gaining is I am having less number of delay blocks. This Z
Okay.
inverse. So these
Okay.
are, the delay blocks are less compared to my direct form 1. So here
Okay.
where I am gaining it. This is
Okay.
very simple representation. This is the very starting representation of my system. So can I get better in order to have a simple circuitry, a more concise circuitry where I will require less number of components. So that is the
Okay.
main purpose of realizing any
Okay.
system.
Okay. Okay. So direct form 2 is a better thing than direct form 1 by having a less number of delay elements.
Yes.
Okay. So direct form 1 is straightforward, so you can understand. Direct form 2 is 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 an H2Z into H1Z, whereas direct form 1 is H1Z into H2Z. Okay.
Yes.
Okay. Okay.
It is
Okay.
same thing. You'll get same input for same output for same input for all the representations. The only thing is the purpose of doing it will be different in each case.
Okay. So subsequently, that the other parallel form and all will have better other advantages, right? So more advantages. Okay, go ahead. Go ahead.
Okay. So now let us look at the another thing, that is
Cascade form. Maybe what is the next form is cascade.
no direct form 1 transpose and direct form 2
Ah,
transpose form.
yes, yes.
Okay.
One general question, madam. So, for IAR filters are basically the rational expression, right? That expression h of z should be rational. The power of a numerator must be less than the power of the denominator. Am I correct?
Yeah.
Okay. Then only we can realize IAR filters.
Even if your power is greater than, you can realize it, but that system may not be a causal system.
Oh, okay. Okay. I'll keep in mind that. Okay. Thank you.
It depends, like what is happening. So
And and if the expression is just a polynomial, then that becomes FIR system. Correct.
correct, correct.
Okay.
FI
Okay.
system, and it's if it has to be causal, then your exponents, like the exponents of z, should be negative or 0.
Okay. Okay. Okay, madam.
Okay, so let us now look at the direct form 1 transpose. So what we are having here is we have this hz is equal to 1 plus 2z inverse upon 1 minus 3z inverse plus 2z to the power minus 2. Then what I can do is I can write this as yz is equal to xz multiplied by 1 minus 3z inverse plus 2z to the power minus 2 multiplied by 1 plus 2z inverse. So this is the first system that I will realize. Now again it is the same thing that we are realizing, but now this is here also I was first realizing this part which is exactly the same, but now what we'll do, we'll interchange the position of this delay block from here to here, and if we do that, then in that case we'll get the direct form 1 transpose. So I'm just changing the position of this delay block from here to here and nothing else. So these are just different ways of realizing any system. Sometimes one representation is better, sometimes another representation is better. It's simply a realization format, a standard format to realize a system. Like if I'm realizing, I'll look at these forms. So let's do direct form 1 transpose. So I'm realizing this part first, this denominator part first. So I'll have xn here, then this gets added to something, then I have a gain of 3, now a delay block of z inverse which gets added, then again I have of minus 2, gain of minus 2, a delay block z inverse, this gets added here. So this is the first part, and after that I have, this is my, let's say, wn. Now this wn gets added like this, and I have gain of 2 z inverse this. So this is my direct form 1 transpose representation. It is same representation, the same way that we have done here. The only thing is now the delay that is available here will now be available here.
Okay. So,
Nothing else.
okay. Okay. How could we do that? By looking at expression. Yeah, somewhere.
You can look at this part here. Let's say this is my wn. Then
Yes.
this point here. So this will be again wn, right?
Yes.
This also be wn.
Yes.
So here, this point, at this point, what will I get? Minus
Yes.
2 times wn minus 1, right?
Yes.
Now
Yes.
at this point, what will I get?
Yes.
Minus 2 times wn minus 1 multiplied, plus 3 times wn.
And yes.
Now, now at this point here, what will I get at this point? Let me use some different color. This point, what will I get? This entire thing is getting delayed by 1 unit, so it will be minus 2 times wn minus 2 plus 3 times wn,
Yes.
and this gets added with xn, and this
Yes.
was the equation that was for wn.
Yes.
See,
Yeah. Same equation. Okay.
same equation, and then this wn that we have obtained gets added with 2 times wn minus 1.
Yes.
Okay, so this wn that we are getting here, that gets, now here what I am having is Wn multiplied by 2. So this
Yes.
Yn that we have obtained is basically Wn plus 2 times Wn minus 1. So does this representation make sense to you?
Yes. Yes.
Okay. So here it's basically Wn minus 1. It is same equation. See, Yn
Yes.
is Wn plus 2 times Wn minus 1 and Wn is given by this equation here.
It's exactly same as the DF2, right?
It is exactly same as df2, but the only difference is the position of my z inverse.
Okay.
Here it was located here, it at the common branch, but now it is shifted here.
Okay. Okay.
It is just a way of representation, nothing else.
Okay.
And the other way of representing using the transpose fashion is df2 transpose. Now the way we had done df2, the normal one, we had interchanged the things. So similarly here also we'll interchange these two things and obtain it same way, in a very similar fashion. So this is my first system, this one. This one I'll construct first, and after that I'll construct this one. So let's do it. So what we are having is my xn goes here, okay. So this is xn, then I have a gain block of 2 units and a delay block, something like this. And then I have yn here, then I have this adder is common here, so I'll have a gain block of 3 which goes here and delay again, and then I have a gain block of -2, a z inverse block here, something like this. So this is my direct form 2 transpose. Now if we compare my direct form 1, I had 1 2 3 adders, but now I have only 2 adders, so I am having less number of adders compared to the direct form 1 transpose.
So, what did we achieve here? Advantage over DFIT.
In df1 transpose, how many number of adders do we have? 1 2 3, 3 adders, and in df2 transpose I have only 2 adders.
Okay, so slowly, so we reduce to 2 adders and 2 delay elements. 3 adders and 2 delay.
Correct.
No?
No, 2 adders and 2 delay elements. I have 2 delay elements only.
Yes, yes. 3 delay elements, right? Sorry. Okay, okay.
1 2
Okay.
3, 3 delay elements here and 2 delay elements here.
Okay, yeah, yeah. But the amplifiers remain the same. I think amplifiers won't change, right? In any case.
Amplifiers won't change.
Yes, yes. I got it. Yes.
Okay. The next way to represent any system is this cascade representation. So what I have here is hz is equal to 1 plus 2z inverse upon 1 minus 3z inverse plus 2z to the power minus 2. This I can write as 1 plus 2z inverse upon 1 minus z inverse into 1 minus 2z inverse. So this I can write as 1 plus 2z inverse upon 1 minus 2z inverse multiplied by 1 upon 1 minus z inverse.
So here we are assuming that denominator is factorizable.
No, no, it may or may not be. It's
So
fine.
if it doesn't, then what we do?
Then you just split it into two parts and apply your cascade. Like you try to reduce it to the most simplest form.
Okay.
Like it will change from your system to system.
Okay. 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 So in cascade form, first we have to examine whether the denominator is factorizable, and if so, we divide it into two expressions, two rational expressions.
Yes.
Right. Okay.
So let's say this is h1 of z and this is h2 of z. So we'll construct h1 of z using direct form 2 because it was giving me a benefit of having less number of degree elements. So what do we have here is we have xn. Now this xn, then I'll have an adder block here, a delay unit, z inverse. Then this is minus 2. This we are realizing first this part. So since we are having minus 2, it will get changed by a factor of 2, like a negative sign, like this. And then I have 1 plus 2z inverse. So this will get added. Something like this. So this is my h1z. And now I need to realize this h2z using direct form 2. So this is my input. I have a adder here, then a delay block of z inverse, and a gain block of unit amplitude. It gets added, and this is y of, and this is my h2 of z. So this h1 of z and h2 of z are represented using the direct form 1 representation, direct form 2 representation.
So cascade is nothing but direct form 2 representation for both H1Z and H2Z.
Generally what happens, it may be a case that this system block, the block for this system is available and the block for this system is available.
Okay.
So instead of reconstructing the entire system using direct form 1, I can directly use these two blocks by just cascading them.
Okay. Because why the word cascade? In fact, this cascading we are using in all the forms, right?
Yes, but here what the main purpose is, I am having this system here, its block is available.
Yes.
Then suppose I have this block h1 of z.
Yes. Okay, okay. We cascading H1 of Z with H2 of Z. Z, right. So that is the meaning of cascade form.
Yes.
Okay. So yeah, if you have another one H3 of Z, then we can add that also.
Yes.
So cascade definition is two transfer functions, one after the other.
Yeah.
Okay. Okay. So in earlier case, in a DF form, those were not actually cascades.
No.
Those were representations.
Yes. I am representing the entire system. I am not dividing it into subsystems.
Yes. Yes. Okay, I got it.
Okay. After that, the next part is parallel form 1 and parallel form 2. So similar to the cascade system, so suppose I have some blocks which are available to me uh, in this form. I can cascade them. Similarly, I can have a parallel representation which goes something like this and add all of them like this by adding an adder block. So this is known as parallel representation. And there are two forms of doing this parallel representation, and the first form is parallel form 1. For parallel form 1, so let's start with this parallel form 1. For this we do partial fractions in terms of z inverse. So let's start with parallel form 1, and for this we do partial fractions. So this uses partial fractions in z inverse. So what do we have is hz is equal to 1 plus 2z inverse upon, we had seen the factorization of this, so it was 1 minus 2z inverse into 1 minus z inverse. So this I can write as a upon 1 minus 2z inverse plus b upon 1 minus z inverse. And this I can then, in order to find this a and b, I can write it as 1 plus 2z inverse is equal to a into 1 minus z inverse plus b into 1 minus 2z inverse. So to find the value of a, let's say z inverse is equal to 1 by 2. So what I have is 1 plus 1 is equal to a into 1 minus 1 by 2. So this implies that a is equal to 4. And in order to find the value of b, what I'll do, I'll put z inverse equal to 1. So it is 1 plus 2, that is 3, is equal to b into 1 minus 2. This implies that b equal to minus 3. So what I have is hz is equal to 4 upon 1 minus 2z inverse plus minus 3 upon 1 minus z inverse. So this is my h1z and this is my h2z, and these two are to be added. That is, I'll connect those in parallel and add them. So now let us first construct this one, that is 4 1 minus 2z inverse using again direct form 1. So what I have is, let's say this is xn, this gets added. So I have a z inverse block multiplied by a gain of 2. This gets added here, and then I have a gain of 4 here. Another system that we have is this xn. This gets added, so I have this z inverse block here and a unit amplitude gain block here, and this gets scaled by a factor of minus 3. So these two are basically having the same input, that is xn, and the output of these two is basically getting added. something like this. So this is my parallel form representation. So this system is my H1Z, and this is my another system that is H2Z. So let's say this is H1Z, this one is H1Z, and this one is H2Z. So this is my H2Z. Any questions?
So only for parallel form, we have to start with partial fractions,
Yes.
and so that we can express something x1z plus x2z plus x3z like that.
Yeah.
Okay.
And another parallel form is basically parallel form 2. And this parallel form 2 uses partial fractions in Z. So for that, what we are having is HZ. Okay. This HZ, I can simplify it as Z into Z plus 2 upon Z square minus 3Z plus 2. So this I can write as Z square plus 2Z upon Z square minus 3Z plus 2. Now this I can write as, simplify as Z square minus 3Z plus 2. I had added minus 3Z plus 2, so I'll have to compensate it. So I'll have plus 3Z minus 2, and this 2Z was already here, so it will be 2Z whole divided by Z square minus 3Z plus 2. So this I can write as 1 plus 3 plus 2, 5Z minus 2 upon Z minus 1 into Z minus 2. Now what I'll do, I'll try to obtain the partial fractions for this part. So what I have is 5Z minus 2 upon Z minus 1 into Z minus 2 is equal to A upon Z minus 2 plus B upon Z minus 1, and this I can write as 5Z minus 2 is equal to A into Z minus 1 plus B into Z minus 2. So let's say Z is equal to 2, then this is equal to 5 into 2, 10 minus 2, that is 8 is equal to A. Similarly, if I have Z equal to 1, then 5 minus 2 is 3 is equal to B into 1 minus 2, that is equal to, which means that B is equal to minus 3. So what I have is this HZ is equal to 1 plus 8 upon Z minus 2 plus minus 3 upon Z minus 1. Now in order to get it in terms of my delay block format, what I'll do, I'll divide and multiply and divide these two parts by Z inverse. So what will I have is 1 plus 8 Z inverse upon 1 minus 2 Z inverse plus minus 3 into Z inverse upon 1 minus Z inverse. So what I have is, this is my xn, this part is my xn as it is, then this xn will go here and it will be added with a delayed version of this part, which is multiplied by a gain of 2, that is direct form representation of this system, and this is again multiplied by 8. This will get added like this. And another thing that I am having is this third block. So what I have is xn getting added with a delayed version with a unit gain, that is this one here, and it will be amplified by a factor of -3. This gets added here, and this is my yn, this is my xn. Any questions?
So in all these forms, which one you think is the more optimal in terms of elements? Is parallel form 2? No.
No, it's not like optimality we can comment for my direct forms. These are
Okay.
like if I'm having this system z inverse upon 1 minus 2 z inverse already available, then I'll
Okay.
go for this. But if I
Okay.
have this system available only 1 upon 1 minus 2 z inverse, then I'll go for this. So based on
Okay.
availability, I can modify my realizations.
So what you are saying is that some filter blocks ready-made are available. Then
Yes,
we use this form. Yeah.
yes,
Okay. It's mainly for construction. That is how we use these structures.
yes. These structures help you in implementing this system physically.
Okay.
Yeah.
Okay.
So this was the one example for this direct form, all the representations. I'll take one more example, last example. Sorry. Yeah, I'll take one more example for the system representations. And again, for all the 7 forms will represent, will use to represent, will represent the system using all the 7 forms of realizations. So the first one that we have is direct form 1 and direct form 2. Okay. So
Uh,
here,
Madam, this function is looks similar to the previous one, right? Is also rational only.
yes,
So in what way this would be different? Example, similar example.
it is a similar example.
Okay, because
All
I
all of your systems will be always in your rational form. So they will be similar form only.
okay, because I have seen some models where the denominator is a multiplicity, right? Okay,
Multiplicity of what?
maybe some square. Okay, one minus a z to the power of minus one square kind of thing.
It's okay. You repeat the like okay. If you have something like this 1 upon 1 minus z inverse square, you'll have to
Uh,
write it as 1 minus 2 z inverse plus z to the power minus 2 and realize this.
okay, 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 okay,
And in
madam.
cascade, you can do 1 minus z inverse into 1 upon 1 minus z inverse. You have this block, just repeat it twice.
Okay, okay, madam.
It will all the forms will be in your rational form. So all the examples will be very similar. Any questions?
No, no, but the same method, right? No, absolutely no difference.
No
Here the fact.
difference. Same method.
So here the denominator is factorizable.
Yes.
Yeah. How do we know it's factorizable? So I think the basic high school math.
Yeah.
Picture. Okay, madam. Go ahead.
Okay. So what do we have here is yz 1z is equal to 1 plus 2z inverse plus z to the power minus 2 upon 1 minus 1 by 4 z inverse plus 1 by 8 z to the power minus 2. So this I can write as Sir, can you please mute yourself? Thank you. Yz into 1 minus 3 by 4 z inverse plus 1 by 8 z to the power minus 2 is equal to xz into 1 plus 2 z inverse plus z to the power minus 2. And this I can write as y of n is equal to xn plus 2x of n minus 1 plus x of n minus 2 plus 3 by 4 y of n minus 1 minus 1 by 8 y of n minus 2. So what I have is, I have this xn, which is as it is, it gets added with a delayed and scaled version of x of n minus 1. So it is z inverse, which is delayed and scaled by a factor of 2. Then again I have x of n minus 2, which is scaled by a unit magnitude here, and it goes here. Then I have my output yn so it gets delayed z inverse, then it is scaled by a factor 3 by 4, then I have z inverse and a factor of minus 1 by 8. So this is the direct form 1 representation. Now if we can construct the same thing even without looking at this equation that we have obtained here. Just by looking at this, we can construct it directly. So just look at this numerator part. So this numerator part will appear first here. So what happens is this is 1. Then I have a z inverse block, and the z inverse gets scaled by 2 here. Then I have another z inverse, and then I have a gain block of 1 here. So this will construct my numerator part. Similarly, I need to construct this. So this one is yn, then this z inverse. Now instead of using minus 3 by 4, I'll have a 3 by 4 factor here because it gets shifted to my RHS while writing this yn expression. So this is 3 by 4. Then again I'll have a z inverse, and then I'll have this 1 by 8 but with a minus sign which again gets added. So there is no need to construct or get to this equation. By just inspecting this one, we can get to this representation here.
Okay, great, madam. So that means, so first look at the numerator of h of z and start from left, and then look at the denominator and start from right and inverse.
Yeah, correct.
Inverse. Okay.
So this is my direct form 1. And once I know my direct form 1, I can just interchange these two to get my direct form 2. So for that, what I have is, I have this xn gets added. Then I have this delay blocks, z inverse. 2 delay blocks I have. Then the first one, here I have 3 by 4. And minus 1 by 8. Then here it gets multiplied by a factor of 2. And here also I have a factor of 1 gets added like this. So this is yn. This one also I can draw it just by inspection. Instead of starting with the numerator, I'll start with denominator. So I'll start with denominator. I'll have this xn here. Then this is one factor which I have here. Then this z inverse, a delay block of 3 by 4. Then I'll have this yeah z inverse here, and then this 1 by 8 with a negative sign and these adders. Similarly, then I'll look at the numerator. I already have this z inverse. I'll have a 2 delay block here. One is getting added here itself, and another inverse block, and this coefficient of the z to the power minus 2 here, and it gets added here. So by inspecting this hz, I can directly draw my direct form 2 representation similar to my direct form 1. Now let us look at the direct form 1 transpose and direct form 2 transpose. So for that, what we have is yz is equal to xz multiplied by 1 upon the denominator, that is 1 minus 3 by 4 z inverse plus 1 by 8 z to the power minus 2 multiplied by 1 plus 2 z inverse plus z to the power minus 2. This representation is very similar to my direct form 2. The only difference is I'll interchange these delay, I'll change the position of this delay from here to here. So what I'll get is something like this. So here I have my direct form 1 transpose. Here I'll draw direct form 2 transpose. Okay. So I have xn here, and it will get added to a delayed and scaled version of this factor. So first what I'll do, I'll scale it by a factor of 3 by 4, and then I'll delay it something like this. Then I have this factor of 1 by 8 here, so I'll have a gain block of minus 1 by 8 and a delay block here, adding these two. After that, this is the output of this system here, which will be added here to get my yn, and this is my output as it is 1, and then I have its scaled and delayed version. So it will first get scaled by a factor of 2 and delayed by a factor of 1. Similarly, it will have a delay of gain of 1 and a delay of again minus 2 here. Like these two will combine in combination, will give me a delay of 2 units. So this is my direct form 1 transpose, and the direct form 2 transpose is obtained by just interchanging these two things. Okay, so what I will get is I have xn. This xn will first get scaled by a factor of 2. Then I'll have a adder here, z inverse, and this will get added here, this part I'm drawing. Then this gain will come, so I have 1 z inverse something like this. After that, I'll draw this part. So for that, what I have is, I have this y of n here. This yn will come like this, and first of all it will be getting scaled by a factor of 3 by 4, and then delayed by 1 unit and getting added, and then this will be minus 1 by 8. So this will be getting delayed. This will be getting delayed by 1 unit, delayed by 2 units, z inverse, and scaled by minus 1 by 8, which will correspond to this factor here. And this is my direct form to transpose. Any questions? Okay. The next one is the cascade representation. So here what I can do is, let's say this hz I can write as 1 plus z inverse square upon 1 minus 1 by 4 z inverse into 1 minus 1 by 2 z inverse, and this I can write as 1 plus z inverse upon 1 minus 1 by 2 z inverse, and 1 plus z inverse upon 1 minus 1 by 4 z inverse. So this is my h1z and this is my h2z. So let us first construct h1z using my direct form 2 representation. So what I have is, this xn will get added here, then it will be z inverse I'll have a z inverse xn, it will get added. I have a delay block of 1 unit followed by a gain block of this factor 1 by 2, which gets added here, and then this I have a delay block here, a factor of 1, which gets added here. So this is my h1z, and after that I'll construct this h2z. So this this gets added, a unit delay factor, then I have a 1 by 4 factor here, now this is unit amplitude and it gets added, something like this. So this is my yn, and this is my h2 set, and this is known as the cascade form. Any questions? Okay. If not, then let us look at the parallel form 1 and parallel form 2 representations. So what we'll do, we'll start with parallel form 1 representation, and as mentioned earlier, this is basically obtaining partial fractions in Z. Okay, so let us consider this HZ.
Madam, partial fractions in Z inverse.
Sorry, Z
Right?
inverse. Yeah, thank you. So this is HZ is equal to 1 plus 2Z inverse Z to the power minus 2 upon 1 minus 3 by 4 Z inverse plus 1 by 8 Z to the power minus 2. So this I can write as 1 minus 3 by 4 Z inverse plus 1 by 8 Z to the power minus 2, and in order to compensate it, I'll add 3 by 4 Z inverse plus 2 Z inverse minus 1 by 8 Z to the power minus 2 plus Z to the power minus 2 whole divided by 1 minus 3 by 4 Z inverse plus 1 by 8 Z to the power minus 2. So this I can write as 1 plus, this reduces to 8 plus 3, 11 Z inverse by 4 plus 7 by 8 Z to the power minus 2 whole divided by 1 minus 3 by 4 Z inverse plus 1 by 8 Z to the power minus 2. This I can write as 1 plus Z inverse, inside the bracket I'll write as 11 by 4 plus 7 by 8 Z inverse whole divided by 1 minus 1 by 2 Z inverse 1 minus 1 by 4 Z inverse. Now let us consider the partial fractions for this. So what I have is, so what we'll do, consider 11 by 4 plus 7 by 8 Z inverse whole divided by 1 minus 1 by 4 Z inverse into 1 minus 1 by 2 Z inverse. I can write it as A upon 1 minus 1 by 4 Z inverse plus B upon 1 minus 1 by 2 Z inverse. So what I have is 11 by 4 plus 7 by 8 Z inverse is equal to A into 1 minus 1 by 2 Z inverse plus B into 1 minus 1 by 4 Z inverse. So let's say Z inverse is equal to 4. So in that situation, what I have is, so suppose Z inverse is equal to 4, then this reduces as 11 by 4 plus 7 by 8 into 4 is equal to A into 1 minus 2. So this is basically 14 plus 11, that is 25, which means that A equal to minus 25 by 4. Similarly, let's say Z inverse equal to 2. So what do we have is 11 by 4 plus 7 by 4 is equal to P into 1 by 4. Okay, so this is 18 by 4 is equal to I'm sorry, this is 1 by 2. Yeah. So this is b by 2. So this comes out to be 9, which means that b equal to 9. So using this, I can write this entire expression, this hz, I can write as 1 plus z inverse inside the bracket 9 upon 1 minus 1 by 2 z inverse plus minus 25 by 4 z upon 1 minus 1 by 4 z to the power minus 1. This I can write as 1 plus 9z inverse upon 1 minus 1 by 2 z inverse plus minus 25 by 4 z inverse upon 1 minus 1 by 4 z inverse. So let us try to represent this system here. So what I have is this xn. This is xn that I have, which is going directly to my output. Then this is the first system that I need to represent. So what I have here is this xn gets added with the delayed and scaled version. Here, and this resultant thing gets amplified by a factor of 9. Then now let us construct this one. So I have this xn, this is z inverse, and this gets scaled by a factor of 1 by 4. This is what this is 20.
Madam,
Yeah.
I feel that the mistake in the above 9, the amplifier 9, it is 9 of Z inverse, right?
Oh, sorry.
Should be below.
Yeah, thank you.
Should be below
Here.
that.
Yeah, thank you. Similarly, here also this 20 minus 25 by 4 gain block will come here. These will get added. Is it okay?
Yes.
Okay. Then if this is okay, then we'll go for the direct form, the parallel form 2 representation. So now we'll do parallel form 2 representation. Okay. So for that, we need to get this h of z in terms of z and not in terms of z inverse. For that, what I'll do, this hz I can write as z square plus 2z plus 1 whole divided by z square minus 3 by 4 z inverse plus plus 1 by 8. 3 by 4 z plus 1 by 8. Now what I'll do, since in order to get the partial fractions representation, the degree of numerator should be less than the degree of denominator. So I'll consider hz by z. So this I can write as z square plus 2z plus 1 whole divided by z into z minus 1 by 4 into z minus 1 by 2, and this I can write as a by z plus p upon z minus 1 by 4 plus c upon z minus 1 by 2. So what I have is z square plus 2z plus 1 is equal to a into z minus 1 by 4 into z minus 1 by 2 plus bz into z minus 1 by 2 plus cz into z minus 1 by 4. So let's say z is equal to 0, then I have 1 is equal to a into minus 1 by 4 into minus 1 by 2, so this is 1 by 8, which means that a is equal to 8. The next thing that we have is, let's say this z is equal to 1 by 2. In that situation, what we have is 1 by 4 plus 2 is equal to, this goes to 0, I have c into 1 by 2 into 1 by 1 by 4. So this comes out to be 9 by 4 into, yeah, into 2 into 4, 2 into 4 is equal to c, which means that c is equal to 80. Similarly, let's say z is equal to 1 by 4, so it will be 1 by 16 plus 2 by 4 plus 1 is equal to p into 1 by 4 b into 1 by 4 into 1 by 4 minus 1 minus 2. So this comes out to be, so I can write it as p is equal to minus 8 by 16 minus 8 by 2 minus 8. So this comes out to be minus 1 by 2 minus 12. So this is equal to minus 25 by 2. So b comes out to be as minus 25 by 2. So this b is minus 25 by 2. So what I have is hz upon z is equal to 8 I have 8 plus my b is minus 25 by 2 minus 25 by 2 upon 1 minus 1 by 4 z inverse, no sorry, z minus 1 by 4 plus 18 upon z minus 1 by 2. So hz is equal to 8z plus minus 25 by 2z upon z minus 1 by 4 plus 18z upon z minus 1 by 2. This I can write as 8 upon z inverse plus minus 25 by 2 upon 1 minus 1 by 4 z inverse plus 18 upon 1 minus 1 by 2 z inverse. So now what we have here is this is xn. Now this xn gets scaled by a factor of 8, but let's draw this one first. Okay, just consider this. So what we have is yz upon xz is equal to 8 by z inverse. So this is basically yz is equal to 8xn 8xz, and here I have z inverse, so this is basically yn minus 1 is equal to 8xn, and this gets added. So what we have is xn is equal to 1 by 8 y of n minus 1. I think there is something wrong with this equation. This comes out to be, let me rework this by some another way. I'm getting a factor of z which shouldn't come.
Madam, no, if you are referring to the previous example, suddenly you change the approach, h of z by z. Ultimately, we get everything in z inverse form only, whether parallel form 1 and 2. There is no difference.
Sorry?
You said that the parallel form 2 is expressing in terms of z, whereas parallel form 1 is expressing in terms of z inverse. But if you look at parallel form 2, ultimately the final expression is again still in terms of z inverse only, right?
Yes, but if you look, it was something like this, na 8z. This I can't realize. This is a causal. This is non-causal, so I shouldn't represent it in that form.
Oh,
There is some mistake in my solution which I had done. So
okay.
instead of that, I'll try to do it from scratch. I'll use the same approach that we had considered in the previous
Yes, yes,
example.
yes. Because you deviated, you used
Yeah.
h of z by z form, so I
Yes.
get little confused. Yes.
Yes. So instead
Yeah.
of doing that, I'll just use the same thing. So we had done z square plus 2z. So I'll construct minus 3 by 4z plus 1 by 8 plus 3 by 4z plus 2z plus 1 minus 1 by 8, and I don't know why I am thinking that it will give me similar results as the previous one. So this I can write as 1 plus 3 by 4 plus 2, so this is 4 plus 2 8, 11 by 4z plus 7 by 8 upon z square. So I can write this as z minus 1 by 4 z minus 1 by 2. So what I have, I consider this, so I have 11 by 4 z plus 7 by 8 upon z minus 1 by 4 into z minus 1 by 2 is equal to a upon z minus 1 by 4 plus b upon z minus 1 by 2, which means what I have here is 11 by 4z plus 7 by 8 is equal to a into z minus 1 by 2 plus b into z minus 1 by 4. So let's say z is equal to 1 by 2. So it comes out to be 11 by 8 plus 7 by 8, which is equal to, this goes to 0, b into 1 by 2 minus 1 by 4, this is 1 by 4. So this is 18 by 8 into 4, which is equal to b. This is 9, which means that b is equal to 9. And another thing that we have is z is equal to 1 by 4. So what I have is 11 by 16 plus 14 by 16 is equal to a into z minus 1 by 2, 1 by 4 minus 1 by 2, so that comes out to be minus 1 by 4. So this is basically equal to a equal to minus 25 by 4. is some network issue. Is my screen visible?
Yes, yes, madam.
Yeah, okay, thanks. So this is what I am getting here. So this I can write as 1 plus a is minus 25 by 4 upon z minus 1 by 4. Yeah, it's the same thing that I'm getting. Plus 9 upon z minus 1 by 2. It's the same thing that I'm getting here right now. So what I'm having is h of z is equal to 1 plus minus 25 by 4 upon z minus 1 by 4 plus 9 upon z minus 1 by 2. This I can write as 1 plus minus 25 by 4 z inverse upon 1 minus 1 by 4 z inverse plus 9 z inverse upon 1 minus 1 by 2 z inverse. So if you compare this equation and the one which we had used for direct form 2, it is the same thing. So it's the same thing that we are obtaining for both the parallel form representations. And I think that's because the degree of polynomial in numerator and denominator is same. I am not sure if that is the reason, but both the forms are giving me the same answer in this situation. Any questions in any of the part that I have covered today?
Okay, madam. Okay.
Or any questions in any of the part that was covered in the entire course, because this is the last session that I will be taking, and after this you will have your exam.
Okay. Just a minute, madam. Uh, so generally, you can talk about filters in general, FIR filters, IAR filters. Some properties you can share broadly. FIR filters. Okay. Just to note down summary of.
I think that's not required as such for this course, because
Okay.
this course is not based on filter designing.
Okay.
That is completely another advanced course
Okay.
for filter designing.
Okay. Okay. So yes. So yes. Yeah. Basically, in the entire course, if I look at it, um, the LTI systems are predominantly used in filters.
LTI systems, any LTI system can be characterized. We can say that any LTI system is a filter,
Yes.
because it will have its own impulse response. It will have its own magnitude and phase response. It will reject and pass some frequency. So any LTI system, we can safely say that it is a filter.
It is a filter. Okay. And the filters, depending on the transfer function, we can classify as FIR and IIR. And generally, what they say is IIR filters are easy to implement uh, because of number of elements, because of feedback loop, right? Some statement.
No, it's not like that.
Uh, See, FIR filters have a linear phase response, correct?
Correct.
Correct. Okay.
May or may not have a.
Uh,
It will
yes.
based on how you have designed it.
Okay.
Any FIR won't have, like, you will have different types of filters. Like as I said, that it is completely a different course, like how to design a
Yeah.
linear phase filter and
So,
those stuff.
Somewhere I read a general statement that IR filters are easy to implement than FIR filters. No?
I don't think so.
Okay.
But yeah, okay.
Because what they say is FIR filters, since it is a single polynomial, no feedback loops, so it requires more elements, something like that.
No, I don't think so. That is the case, or that should be the case.
Okay. Okay. So, yes. Say just one thing before we close the session. See, madam, I always get confused about this F domain representation and omega domain representation. In frequency domain, time domain to frequency domain, when you are taking Fourier transforms, because the Aditya sir used F domain, but at some examples we see omega domain. So the formula is slightly changed. The 2 pi sometimes get in the denominator. So is there any general mnemonic to remember one thing and derive from the other? Okay.
I think in this course, Aditya sir has taken omega domain only.
Uh, I,
Yes.
omega domain?
As far as considering his other courses, which include like
Yeah,
maybe
I think,
communication systems course, he gets into F domain, like use frequency, Hertz frequency. But in
yes.
for as far as this course is concerned, he has restricted it to omega domain.
Oh, yes, I got it, but I'm doing both the courses. Can you tell some easy way to translate mnemonic? Okay. You know,
I'll take an example for
uh,
a continuous time Fourier transform. So what
yes,
do
yes,
you
yes,
have is your
yes.
continuous time Fourier transform is x of omega.
You take some duality kind of thing. Yes. Fine. Yeah.
I'll give you a simple, basic, very basic conversion for your basic equations,
Yes.
and that you can clearly convert them or use them for other properties. Okay. So
Okay.
this x of omega is basically integral from minus infinity to infinity xt into e power minus j omega t dt. This is what we have done. Now for f, what happens is this omega is basically 2 pi f.
Yes.
So this x of omega is basically x of 2 pi f, which I can write as xf, and this I'll obtain minus infinity to infinity xt e power minus j 2 pi ft dt. Is this okay?
Yes. Yes. Yes.
Now let us look at the inverse. So this we
Yes.
have done. So again I'll put a tick mark here. So xt is equal to 1 upon 2 pi integral minus infinity to infinity x of omega e power minus j plus j omega t d omega, right? But now I am doing a substitution as omega equal to 2 pi f.
Yes.
So d omega is 2 pi df. So what
Yes.
I have is 1 over 2 pi integral minus infinity to infinity x of 2 pi f e power j 2 pi f t 2 pi df. So this comes out to be integral from minus infinity to infinity x of f e power j 2 pi ft df. This is the inverse transform that I am getting. The 2 pi factor gets cancelled. So if you try to look at the properties in this fashion, wherever
No.
there is a scaling of 2 pi, there won't be a scaling of 2 pi in
Yeah,
the
one thing, madam. Here in this last expression, uh, x of 2 pi f you have written as x of f.
2 pi is not a function. Let's say that x of 2 pi f, I am defining it as x of f.
Okay. 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 You are defining it as x of f.
The way I have done here.
Okay. 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 Okay, ma'am.
Yeah.
So let us consider a duality x of t with capital X of omega and capital X of t. At, yeah, 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 and yes, and in the frequency domain, the same duality is expressed of X of t.
This is frequency domain. This Fourier transform is frequency domain.
Yeah, yeah, it's frequency domain, but in radians, I'm talking about F domain, F expression, X of t in the frequency domain, X of F. This is radians, right? X of t into X of F, and capital X of t.
This is in radians or this is in hertz?
This is hertz, hertz, right?
Right,
Yes, ma'am. Yeah.
right.
And then capital X of t. It is written as X of minus t. Yeah, yeah. Okay. Now, how can you relate them both? Same. Right?
You use this. See, look at this. This is now your expression, right?
Right.
xt is
Right.
equal to integral minus infinity to infinity x of f e power minus j 2 pi ft df.
Yes.
Now replace t by f.
Yes.
Okay, and f by t. Interchange it. So I have x of f is equal to integral minus infinity to infinity xt e power j 2 pi ft df. And now
Yes.
do x of minus f t, sorry. So this will be minus infinity to infinity xt e power minus j 2 pi ft dt. Now this is basically Fourier transform of xt.
Okay.
So basically you go with the first principles. You play with this equation, these equations, the basic equations, do the substitutions and you will get everything.
Okay. Okay, ma'am.
Yeah.
Okay. Thank you, ma'am.
Thank you. Any other questions?
No.
Okay.
Nothing. Thank you very much.
Thank you. If there are no further questions, you are free to leave the meeting. Thank you for attending today's session.